actions, I want to talk about the climate changers. Climate changers are the things that cause the climate to change. So under that one, we'll have natural variability, and things like volcanoes and sunspots and earth rotation and the tilt of the earth and the ocean. Those kinds of things I'm going to talk about in a little more detail and try to give you examples. And then the human actions. The human actions would be things like we do with our cars, and when they manufactured my shirt, we're burning fossil fuels at a fairly large rate. So that's a human contribution to the climate change. The second thing on that score that I want to mention about humans is that we keep changing how we use our land. So we changed from the grasslands and the forest lands of this country into croplands, and we've changed our croplands from rain-fed into irrigated. So we're changing that. Not only that, but we're moving a lot of people into suburbs. So we've changed around Lincoln, a small Midwestern town. We have seen farmland in that vicinity gobbled up by the urban sprawl. So wanted to make note of a few of those things. First thing I'll highlight is the volcano example. And as you look at this, I think you pronounce it Plua. This is a volcano that erupted in December. Now I didn't hear too much about it in the news. I think there was a little bit of comment in the news. But when these erupt, they send huge amounts of dust and gaseous materials up into the atmosphere. So, you don't think about this too often perhaps, but look at all the volcanoes that are active. The red ones are pretty active. The yellow ones are, they're venting and they haven't erupted recently. Black ones would be dormant. But this volcano that I'm showing up above is right down here in this vicinity. So there's Australia, and here's this volcano erupting out there in that island area. So a lot of material gets thrust into the atmosphere, and as you might imagine, that can change things. Certainly we've seen materials from volcanoes drift this way. Volcanoes that erupted in Washington State caused a lot of ash fall across the country, and even further because that material gets up into the upper air. And as you know, we have jet streams that move upper air around the globe very quickly. And so not too many days after one of these erupts, the first move around the Earth has been completed. And of course, that keeps moving around the Earth until it all settles out. So it can be a big climate changer. As shown here by a couple of examples, this would be the percent change in the solar flux. So we're getting sunshine all the time, and if we have a volcano, that drops off. So you can see it looks fairly steady across the 50s, 60s, and 70s until we get in the early 80s and we have El Chacon. So the solar really drops off, and that effect can last for quite a few months and even a year. And you can see that Pinatubo, about 3% change at the largest, and El Chacon around 5% change. So volcanoes happen sporadically. We can't plan for them. We can't stop them. We're going to live with when they erupt, and we won't know the change of those in the future. Okay, so we're going to show some models, how the atmosphere conditions are modeled mathematically, and you'll see those, but they don't include the volcanoes that are going to occur in the future. So keep in mind that we have all this variability going on. Let me change now to the sunspots. Sunspots, when I was growing up, when I was first doing education at the graduate level, people were poo-pooing the sunspots. You know, that 11-year cycle. Well, a lot of meteorologists did not accept that. they did not think we had a, you know, a sunspot thing going on. How could that be? The sun was constant. Well, actually, it's not as constant as we think sometimes when we're growing up. Here's a graph showing variations from our solar, our nearest star. And you can see the blue ones are the sunspot observations. We also have a radiance on here. That would be the amount of energy coming in from the sun. And we have solar flares, which are times when they erupt on the sun, and you have solar flare going out. So the daily irradiance is really quite variable, as you can see with all these yellows going up and down. If you look at the sunspots, the blue ones, then you'll see that there's a few units, like 1 or 2 units from top to bottom, out of this, say, 1,366 watts per meter squared solar irradiance. So they aren't large, you know, compared to the total solar irradiance. 1 or 2 out of 1,300 is not real large. But you see how regular they are. And if you go back, these are reconstructed sunspots going back into 10,000 years ago. So one thing that I like to say is, if you're a doubter about climate change, you have very thin ice that you're on, because it's always changing. It always changes. And we're in a part of the world where it changes even more, because we have the cold air outbreaks that come all the way down from the Arctic. We have the warm, moist air coming all the way up from the Gulf. So we have this great variation in these two air masses coming together very often, moving back and forth. And we have changes from year to year. If you've been around the Midwest and the plains for a while, you know that every year is not the same as last time. It's a little bit exciting sometimes. So another natural variability for us is the Earth's rotation and how we revolve about the sun and the tilt of the Earth. So I think you're probably in touch with this, and I don't have to spend too much time on it. But if we look at summertime, the tilt tilts us towards the sun. Okay? So the sun come in more at a direct angle at this latitude. Now it never gets right overhead, but it gets up to about 23 degrees off of the vertical, or we call it the nadir. And you see in summertime, we're really turned toward the sun, even though the distance to the sun is a little farther away in summertime. In the autumn, we still have the tilt, but we're starting to move to where we're going to have less sun. The sun is going to be over there, further away from us, and going like this. I'm pointing south because it goes further to the south in the fall and winter. In wintertime, the northern hemisphere is tipped away from the sun. So this is a climate change. It's part of our climate. It's an annual cycle. And even as we go around every day, we have that daily cycle. So we have some cycles in this system that we have to know and we have to understand, so that we can separate out any other signals that we're looking for. Okay, if you like, you can ask questions at any time. I didn't mention that, but you're welcome to. If there's any of this that you have a question about, you're welcome to jump in. Now, natural variability also includes ocean and land surface interactions. And it always has. Okay, so we're not talking about man building an interstate highway or something. We're talking about the ocean, which is 2/3 of the Earth's surface. So wow, lots of effect on our climate. A lot of our moisture comes from the ocean. It's evaporated over the ocean. And then we have the land where that air can move across. And I have sort of a schematic here. Get the idea across, hopefully. So here's the ocean over here. Energy comes in from the sun and evaporates a lot of this water. course, it doesn't really warm up that much the ocean. Because anytime a surface can evaporate, a lot of that energy coming from the sun gets used in the evaporation. So we have 2/3 of the Earth, which can immediately start evaporating water, putting it into the atmosphere. Now, it doesn't sit there, right? It doesn't sit there in the atmosphere over the ocean. We have the jet streams, we have the various circulations, the Hadley cells and so forth, that move this air around as we rotate, and we have highs and lows that form. Generally, the land heats up, and so it's an optimum area for heating, moving air upwards, causing circulations like our low and our high pressure systems. But this water, I just wanted to point out that this water from evaporation really affects the climate. And if you're very close to the ocean, like if you're living over near the shore, you get this water vapor coming in towards the shore, and you can have lots of cloudiness. It can be, depending on the currents in the ocean, the currents can either bring cool water, as they do along the west coast, they bring cool water down, or you can be like in the Atlantic, and it takes a lot of water that's warm towards the poles. So it's not just a body of water like I used to think of it, but it's active, it's living, it's doing things, it's circulating. So that's a factor that affects us. The clouds that form as a result of evaporation of the water over the ocean can be carried inland, and when they get about so high, the air cools about so much they get condensation. So we have the precipitation process now starting up. What does that do? All of that condensation releases energy from the water vapor, right? It's now becoming liquid. All that energy is coming off of there. And it was doing something.
Cracking up, Ken.
Crashing.
Oh, atmospheric noise.
I'll try not to dance around too much. There, I'll put it next to my cell phone. Okay, so we're saying that water vapor becomes liquid. All that energy, where'd the energy come from? From over the ocean. We were heating up the ocean and it evaporated. So all that energy went into the water vapor, comes over the land, all that energy is released again. And so it's a great system. You know, we have it bringing water to the lands, but also it's dissipating a lot of the energy on the earth. If we didn't have that water, if we didn't have the precipitation, the clouds, we'd be a much warmer place. And while I'm thinking about it, water vapor is the most plentiful greenhouse gas. So it's also involved in the blocking of sun and the long wave radiation escape. So we see basically, hopefully, that the oceans are quite involved, and the lands have a lot to do with what happens as well. And we're going to look at some examples of this. Yes?
I think what I heard was that water vapor is very hard to model. And so it can or it is or is not used in climate models because it's hard to get a handle on, you know, or even the thought of how can humans affect it, it's hard for us to know. But it is the most plentiful greenhouse gas. So could you just speak to that?
A little bit. Now, Guy is going to talk some about yes, the question is, since water vapor is so important, you know, how is our modeling of it? Is it easy to do or hard to do? Clouds, thunderstorms are on the scale of a couple of kilometers, 2 or 3. The grid models don't know, that is, the grid points are like 100 kilometers apart. So it is kind of hard for us to run climate models and to get the water vapor correct, because so much of our water during the year comes from these convective clouds that don't have a scale as large as the global models. So yes, and I'm going to show a global model in a minute now. That's a good question, and we'll feed right into that. So the next one's the use of fossil fuels. I don't want to dwell on this, but we do have coal plants firing up and using a lot of energy from the coal into our power. So we have a lot of gas being given off from these plants, and that increases what's going on in the atmosphere. The concentration is going up. So top left, carbon dioxide going up. You know, it's 385 parts per million. Nitrous oxide, top right, it's going up. And methane, bottom line, has been going up rather rapidly, but now you see it's tapering off a little bit, but nonetheless still on the rise. CFCs, that's the chlorofluorocarbons down in the bottom right. That's what we used to use in our refrigerators, the freezers, but air conditioners, now they've banned those in most parts of the world, and you can see that that has tapered off. So you can make changes, you can change what happens. Okay, so the greenhouse effect. We're changing the climate, and basically you have the sun bringing all this energy into our world, into the atmosphere. So it's coming down through the atmosphere, a little bit of it gets reflected off into space. It hits the surface, some of that gets reflected. At the surface, all that other energy goes into things like warming the surface, and you have the transpiration. There's a little bit that goes into soil storage, but you know, over a course of a year, it kind of goes in, goes out, goes in, goes out. So what we're worried about is on the right-hand side. I don't know if you can read this, but it says some of the infrared radiation that's re-emitted from the surface is going to go up into the atmosphere. If there is no carbon dioxide there, and no nitrous oxide, no water vapor, that energy is going to escape the Earth's atmosphere, go out into space. But we do have greenhouse gases. We have a lot of greenhouse gases, and that keeps us warmer than if we didn't. So if we didn't have all these gases in the atmosphere, we'd be about 58 degrees Fahrenheit cooler on average, and that would make your summer day maximum sun in probably the 20s and 30s Fahrenheit. So hooray for the greenhouse gases. But now they're getting so large, concentration in the atmosphere, that it's starting to warm. So this is the root of why we think greenhouse gases will cause the planet to warm. Human actions under use of land changes, crop selection, irrigation, and so forth. We have quite a few changes that we as humans have made. So you'll see here a typical picture from the air of center pivots. What I want to say here is that center pivots are putting water onto the land. Part of that water is evaporating. Part of it's going through the plants as transpiration. So we're doing that to increase the yields, but at the same time, we're creating something that's akin to lakes out here, because they're wet during the summer. Off and on they're wet, and there's a lot more water used, like 16 to 20 inches more being evaporated from these fields than what we would get by rainfall in some locations. So modifying the landscape like this does a lot. A lot of the energy from the sun gets used in evaporation. And in fact, we found in these areas that actually the dew point is going up, which causes the minimum temperature to go up, and that the maximum temperature is coming down a little bit. So we can't find climate change per se, like in the maximum temperature, in these areas that are irrigated a lot.
How does the minimum temperature increases affecting agriculture? Can you briefly mention about that. And
Yes.
Repeat the question to the we are recording that.
Yes. Okay. How do the changes in minimum temperature affect agriculture? You may know that crops take carbon dioxide into their system in the daytime, but at night they're losing carbon dioxide. They call it respiration. So what happens is, if you get a warmer nighttime temperature, you'll actually get more respiration, and the more CO2 you lose, then the smaller your factory is the next day to build more leaves, to build more kernels, and so forth. So that part is a negative impact to a large extent. Okay, as we move on, think of all the logging that we've done in this world. Think about the pioneers moving westward, and many of the states were primarily trees until you got to maybe Illinois. A lot of forests. Well, today, that's kind of a mix. There's still some forest left. There's a lot of that land, though, that has been moved into agriculture. And in the mountain areas, the logging, very obvious. And it changes that ecosystem. You have one ecosystem with the trees, you have a totally another one if you change them to small shrubs, bushes, and grasses. So this is another thing that we do that I feel is nearly as important as the actual fossil fuel climate change. It's a climate changer, and in the Amazon, where they're deforestation is going on, they're losing a lot of trees, and it'll be hard to get those ecosystems back. Obviously have an effect on climate change. Very hard to put into a global model. Okay, I mentioned urban areas, and I found this picture of the night lights over the U.S. So this shows how big population centers, you can kind of see the extent of them in a sense. These areas where the lights are coming from are paved. There's parking lots, there's buildings, there's all kinds of urban things going on. The darker areas are primarily not broken up. I mean, maybe they're not in their native vegetation any longer, but they are not covered by concrete. So we move on now to what is a global climate model. And I think, Guy, are you talking about this afternoon? No. Okay. Okay. All right. So I'll give a few details. What they do with these global models is they stack these spheres around the shell of the Earth. So they make multiple levels, maybe up to 20. And each of the intersections, where you see an intersection, that point is part of the model. And mathematical equations are applied at each of the grid points, both this way and this way. So these mathematical models are not the kind that you can solve with algebra and calculus. They're the kind you have to get into like numerical analysis, which means basically that you're trying to integrate ahead just a little ways, like an hour or so, and say what the conditions will be based on where the winds are blowing at this time and so forth. So you can kind of see maybe how that works. Before we said the resolution of thunderstorms is only a few kilometers, and these things are maybe hundreds of kilometers. Even the regional ones are maybe 30, 20 kilometers. And in between that distance, like 20 kilometers, might be from here to Syracuse up the road. So there's a lot of things that can happen in between that. And with our grid points, we can't actually describe all those things. So we have these global climate models. We can use them in the historical periods. So here you see global models. At the global scale, we're looking from early 1900s into this current time frame. So what they've done is they've run these models And if you look at the bluish imprint, that's the result of running different models for the natural conditions. Okay, so that's not adding any greenhouse gases into the model. It's just what it would have done without the greenhouse gases. The other envelope that you see that follows that lineup, that's what happens with greenhouse gases in models. So what we're seeing here is the difference between no fossil fuel burning and fossil fuel burning. So you can see we're looking at maybe 0.5, 1 degree. And if you look at North America, top left, you'll see that we're generally increasing. The black line is the observed. So that's the actual data from on the ground. You've got real data, and it's going up. There was a little downward trend there in the 1950s. But in general, going up, and the blue one going more or less across, but jiggling up and down a little bit. So the reason you have that spectrum or that wide color going through time there is because you're running different models. Different models from Europe, from the US, from Argentina, wherever. But you run, say, 20 different models, you get 20 different results. But without the greenhouse gas, they're all agreeing it's not going to change much. With the greenhouse gas, it's going up. So there's the global scale, and we can see down to continental, basically, on the top left. Well, let's get a little closer. We'll just look at the U.S. now, and actually North America, but Central North America is in the bottom, in the middle. So this is, again, running those multiple models, and look how tight they are to the black line. Pretty close. Models can represent what has happened historically up to now. As you go out into the future, top or the bottom middle one was Central North America, and you'll see that it's predicting an increase. And when you get into the 2100, even back up to the 2050 time frame, you can see it's around 2 to 4 degrees change, and this is Celsius, so that's almost double that for Fahrenheit. Okay, so models are saying that we're going to see a change. The little bars, I can show you these bars here, those are for different scenarios. So as we look into the future, what they say is, okay, what if greenhouse gases go like this? Or what if they go like that? So each of those, that's a scenario. And these scenarios range from up here near, let's go over to this one, near 8 degrees Celsius for this particular scenario down to 4. And then for this one down here, it's more like 2 to 5, something like that. So scenarios, that's what you think is going to happen to CO2 in the future. And then these are the results from many models to try to verify what will happen. This is to illustrate to you how the different seasons are going to be changed. So on the left-hand panel, those are annual results. Middle, that's December, January, February, and then on the right is summertime. So if we start on the right here, we'll see summertime, warm temperatures. If we look here, on precipitation, you'll see this 0 to 5, and then over here is 5 to 10. So we have some increases expected here. If we go down to the left here a little bit, no, decreases. If we go into our southern plains, this is showing decreases. In wintertime, some increases in here are seen in precipitation, but a lot of red. So we're looking at warmer temperatures and maybe a little higher precipitation. This down in here is telling us how many models are showing a greater than result. So the temperature is increasing. How many models say that? Well, right in here, 21 models are saying that. If you go into here, if you go into this white area down at the bottom, that means that only like 8 to 13 models have the increase, and the others show decrease. So in the areas where you don't see very many on the bottom panel, that means the models are disagreeing about what's going to happen. But we still need to be prepared, because one thing could happen or the other. And climate has always been changing, and everybody around agriculture knows that that's been important in the past. So the very warm nights, this comes back to that question. What happens when we have warmer nights? And we said in the irrigated areas we're going to have that for sure. It's already happening. These warmer nights are associated with higher dew points. When you irrigate, you increase the dew point of the air. So at nighttime, how low can the air temperature get? It can get down to the dew point. And a lot of times, the minimum temperature is a good estimate of the dew point. You can't really go lower than the dew point until you condense a lot of water out of them, and then it can start to decrease again. Okay, two scenarios here. A low emission one here, and a high emission one here, indicating the percentage increase in the very warm nights. Okay, I'm just going to show you a few results in these various ones. This is another result that's coming both from the data and from the models. What we're looking here at is we have the precipitation distributions. You know that we get little tiny showers, we get a trace of precipitation, all the way up to 6 inches, 7 inches, the flooding kinds of results. So, in this graph, when you're going from left to right, you have the light precipitation on the left and the heavy on the right-hand side. What this says is that we're going to have fewer of the light precipitation events and more of the heavier precipitation events. Percentage change on the vertical axis. So out on that end where there's 6 or 8 inches of rainfall, you're going to get up in the neighborhood of 30 to 40% more of those events than we're getting now. And this was attained by looking with the models across the conditions from 1990 to 2009. Any questions on this one? It's a little bit hard to understand, but it's well worth looking at because more heavy rains. Observations actually show this. So it means more of those big thunderstorms that process all that energy. The storms on the right, the energy processed by those storms, one big thunderstorm could be like 50 A-bombs like they dropped on Hiroshima, 50 of those. So this is a lot of energy leaving our atmosphere through thunderstorms. Yes, Randy?
And is the coverage area decreasing as we see these thunderstorms race from southwest to northeast rather than just settle in and give you widespread coverage? Are we going to see lesser coverage?
Okay, Randy's question is basically whether these trends here for more heavy thunderstorms are consistent with more coverage or less coverage. I think the answer is still is uncertain. I don't really know, but the mesoscale systems that we have in the plains usually deliver the most rainfall. I mean, a system that may stretch from Sioux Falls down across Grand Island and move across into Iowa. Those are cumulus convective clouds that are processing lots and lots of moisture and putting quite a bit of water on the ground as they travel across. they're not quite as consistent on the ground as the big soakers that we get where we just settle in for 3 or 4 days and it rains. But cumulus on the whole is responsible for a lot of the water that we get. I think the bigger storms will still be in these mesoscale complexes that move across. That's where I think they're going to be given birth. So I think you have a coverage issue, a little bit up in the air, but these things, maybe they'll move faster, I'm not sure. It's pretty complicated about how a thunderstorm actually moves. It moves to seek out the energy that it needs to keep going. And it won't move into a dry area, that sort of thing. Really good question. I'm interested. Give me some money in return. Okay, so climate affects our crops, right? Here's a corn crop, different stages of development, all the way from the emergence on the left over there, through final maturity on the very right. And these, when you see the tassel forming up here next to the seed area, you see there's a tassel here. So that's a really sensitive stage. Pollination, critical to getting those ears fertilized and getting those seeds going. So, what does this illustrate? It illustrates that crops respond to temperature, and in certain critical stages, they're very sensitive. So, if we're talking about pollination, sensitive stage. All these stages in here, right in there, are also sensitive because this is when you're filling up that kernel. So if you're short on moisture at this stage, bad news. Very sensitive in this area. So climate change, on the whole, will depend on how it's expressed in time in the summer. Not only how warm it gets, but also how it, timing-wise, how it develops. So there's 2 rows down here in the bottom that I want to show. This row here is accumulated degree days. If you haven't been exposed to that, a GDD, or growing degree day, is the average divided by 2 minus 50. 50 because corn crop doesn't really respond much below 50, but as it goes up above 50, it responds faster and faster. So we start accumulating these back here in the vegetation stage, 80 and so forth. And when we get to the end of the season, for this cultivar, for this hybrid, it's 2450. Now for other hybrids, you can choose longer ones. And people do. I think by experimentation, they're growing the longest season hybrids that they can. If they go longer, what happens? Freeze. Right? Freeze on one end or the other. If they go shorter, they lose yield. They're really safe, but they lose yield. Shorter season hybrids do not produce as much yield as the longer season hybrids. So now we bring temperature into the situation, and it depends, with the temperature, depends upon how warm it is as to when you get here. The warmer it is, the faster you get to this maturity. So I think there's some thinking that we need to get rid of, that we're going to have longer growing season. Yes, we'll have a longer freeze-free season, but not necessarily good, because the crop, if you stick with maturities you have now, maturity groups, then you may be mature much earlier in the year, but you won't have spent very much time in these grain filling time periods. That means the grain won't get as full. So another climate change that has to do with our warming would have to do with how fast the crop gets done and these grain filling periods. And crop models are being developed, and Guy will hopefully tell us more about that this afternoon. But they're being developed to handle this, to simulate this, so that we could say, okay, you guys in York, Nebraska, you are growing this hybrid. but it's getting warmer. So our models say, go to this hybrid, go to this longer season hybrid. And of course, the similar type of things can be done for soybean or wheat and some of the other crops. Okay, so I wanted to point out kind of the rise of climate through a plant. Now, this illustrates how we get to maturity. Okay, so I've got several axes here, but this is the change in maximum temperature, and this is the change in minimum temperature. And this is just 1 year's data, and we're growing at 2450 GDD corn, like in the last example. So if it gets warmer by 3 degrees for both max and min, we're out here on this corner. And that means that the season's going to go down. Harvest is going to come a whole week earlier. Okay? So you didn't have as much time in that grain field. If we go to a -3 and a -3, this is just a cooling scenario for fun to get a range. But you could go to 10 days shorter. I'm sorry, longer. Keep me straight. But the cooling would cause for longer seasons because the GDDs would be less each day, and the growth stage accomplished at a slower rate. So from 10 down to 18, there's a range maybe of around 18 days for these crops, like 2450 GDD corn, in the time that it would become mature. Okay. I guess I'll show a couple of examples here of water use. So there's been questions about what's going to happen to the max temperature, what's going to happen to the min, what's going to happen to the dew point. But what's going to happen to the water use? So you can imagine that higher temperatures cause greater water use. That's everybody's experienced this. However, you're not going to go as long. So with those higher temperatures, are you going to have less water use because you didn't go as long, or more because you had higher temperatures? So there's a lot of feedbacks and problems in trying to do this work. In this example, I have two hybrids. I have a 2600 GDD hybrid in the top panel and a 2800 in the bottom. So the 2800 would be a higher yielding, and it would take longer to get to maturity. Looking at the planting date and ranging from 30 April to 25 May, so almost a month, a spread across here, decided to go through and analyze what was the crop water use. And keeping the temperature constant, not simulating a warming or a wetting or warming, either one. But if you planted on April 30th, you'd have about 18.68 water use, inches water use for crop. If you wait to 25 May, then you get to 17.85. So this has to do with when you plant in relation to the hottest, driest part of the year. If you plant when you're back away from that, then your factory, your corn factories, can get bigger sooner, and it'll want that water earlier, and it'll go all the way through the warm period with that bigger factory, so it's going to use a little more water. If you wait till later to plant, the corn will still be growing when you hit that highest part of the year, so it won't use quite as much water in that stage because it won't be big enough to use that water. So it turns out that sowing dates, early ones use a little bit more water and late ones use a little less. But if you want to have safety, you want an early planting date to get this thing off to a good start. So it costs you a little bit in irrigation, but you get it off to a good start and get it through the growing season. If you keep it watered, get it through the growing season without stress. Now the 2800 down here, the plant 30th April, you have 20.43 compared to 18.68. Same day of planting. So the larger the GGD, the longer the season hybrid, the more water you will use. And as you go to later planting dates, again, that goes down. But you want to look at your difference here between these numbers, like 1868 for that hybrid and 20.43 for this one. So one of the adaptation processes, one thing you could do to adapt would be to grow these longer season hybrids because it's warmer. It will take them longer to get to maturity, but it'll keep a nice long period for the grain fill. So that might be a possibility. What will it do to irrigators? Cost them more money, cost them more irrigation. And changing from 26 to 28 could give a difference like 2.4 inches over the whole season. So what is that? That'd be like at least 2 irrigations. And $8 an acre, you know, it's going to take $16 per acre more to get this second crop through. Oops.
I have a question.
Yeah.
I'm further south, but if we push planting dates back those are way back for us anyway, but pollination at the wrong time of the year can cause us major havoc with our high temperatures. Is that a concern with pushing back in Nebraska?
So the question is, when you plant determines when you'll go through pollination. That's a very sensitive stage. So will moving the planting date this way cause you a problem with that sensitive stage? Because maybe high temperatures are more prevalent then and so forth. Yeah, I think this is where the crop models come in to give us a better feeling for when will the pollination take place in our climate. We're further north, it might be a little bit different for us and so forth. Randy, did you have a comment?
Mike, tell me if I'm wrong here, but we're seeing different strategies on dry land versus irrigated. And in our area in southeast Nebraska, we're tending to have guys go earlier to dry land planting. They plant for dry land corn first, and they're going with shorter season varieties on dry land. And Mike's shaking his head. He's all seed over there. But it's a different strategy going on right now with dry land versus irrigated. And
So the dry land guys, they want to get it through those stages.
they're planting their dry land corn first and
Early.
earliest. And they
Okay.
tend to be not long season hybrids. They tend to be more mid to short.
Randy, that'd be similar, you guys do
That's
southeast
in
Kansas,
Southeast
right?
Kansas.
We plant
for
about the
30 years.
20th of March and try to get a roast here by the 4th of July.
Yeah, you guys are harvesting in August,
Last
and you're
year
putting
was July.
105-day corn, and then you'll go from Nebraska, which is all the way up to 118, and then you go back down in southeast Kansas, which is unique. 'Cause
We're very unique in some of these.
and that's why you plant beans late down there too.
We
The
plant
opposite
beans
late.
late.
But Nathan, in
That's
South
it.
Dakota, you're planting longer growing degree varieties than what you've ever done.
Yeah, so I'm saying it's unique, there's some unique geographic differences in hybrid selection, for sure.
There's one danger to all of this. It's fine as long in this part of the country, your fall and your spring moisture, to the point that you can supply an available amount of water. The strategy fails as you move earlier because in the long run, you're missing out on some of that recharge.
And it had full profiles.
Yeah, that's your key issue. What are you planning and what you're managing? Because you're basically extracting moisture out and you're shifting the whole water balance. And this year was a different example as last year. So that strategy really possible.
Our soils are so shallow, our area agronomists used to say we were no more than 2 weeks away from the drought or 6 hours away from the flood.
Yeah. These are very important comments. The strategies, you know, the value of doing this thing. Is it a good thing to do for your area or not? And the fact that it won't work the same across our corn belt, I think, you know, as we recognize that, and then as we start talking about strategies, we'll be able to prepare our clients, or prepare farmers for different strategies in different regions. And eventually the risk associated with these different strategies. I have done some analysis where I've looked at, you know, at a given location, how far can you push the cultivar down? How many GDDs can you go to? 2,600, 2,800, 3,000? Because each time you go a little further, you get closer to those freeze dates on each end, and eventually you get into them. And I have found that in some of our work with corn. We're redoing soybean phenology. Our growing degree 81 doesn't work as well with soybeans. So the one that we have on our center's interface right now doesn't work as well. We're trying to work with Jim Speck at the University of Nebraska and his soybean team to put up a new phenology that works better. So we'll talk more about that, and we'll run more simulations to look what happens with soybeans if we try different strategies. But I hope those kind of things continue into the afternoon. I think, Japan, that's why we're doing this, right?
Sure.
We want to know these things. Another thing that's hard for us to deal with sort of is to take out the climate change signal from the hybrid improvements. So crop breeders have been working on better hybrids, and over the years from 1960 here to 2010, we see that the yields are generally trending up. We often say that's better hybrids. But as we've talked about, a lot of other things are happening in these years. A lot of things are labeled there. Wet spring, early frost, light, drought, flood, and some unusual climate events, including high temperature, very high temperature events. So weather's having that impact through here, through this time period. But the crop breeders have been able to give us better hybrids, higher yielding hybrids. There's some questions about how far that can go. Okay. So far, it's working great, and they've had great success in giving us hybrids. As the climate begins to change on us, we're going to have to keep our eye on those hybrids that are appropriate for our area. Okay. Let's see. My impact slide. So here are some things that either are happening now, showing up in the data, the models have said are going to happen. So on the left-hand side, you'll see those kinds of things. If we have a warmer summer, that means we'll have a longer freeze-free season. But the warmer the summer, the faster the different phenology stages go by. So we'll have an earlier harvest, earlier maturity harvest in warmer summers. In addition, we should see more water use, higher water use. So those are three impacts already from just warming the summer. If we have the higher frequency of heavy rainfalls, we'll have increased runoff in most areas. We were talking at breakfast about terrace farming and how some people are actually pulling their terraces down. But with these heavier rainfalls, that's not wise. We should be looking for ways of planting those runways, those runoff areas, with plants that withstand the runoff and hold the soil in place. So we could see soil erosion, we could see loss of fertilizer and nutrients and so forth in the soils as an impact to these higher frequency rainfalls. Warmer nights in the summertime, greater respiration. We're going to lose CO2 at night out of the leaves, and That will change how our factory works. Air becoming more moist. Well, it certainly is in irrigation areas, but overall, if we push the ocean harder with more energy, we're going to evaporate more water. More water coming over the land will mean higher humidities. If that's true, then we'll see the increase in some diseases. I think you know that certain crops are not grown in the eastern part of our country, maybe a little bit, but you get some diseases associated with those high humidities, and it's just too much of a fight. I think wheat doesn't do that well if you go east of the Mississippi, for instance. Of course, corn is a better cash crop, so maybe there's some economics involved as well, but diseases may be more prevalent. And then in the wintertime, if you have cold winters, you do kill out some of these pests. Yeah, if you're looking at corn borer, some of those things, if you had a good hard winter kill, you'll have less corn borer in the next summer. So increases in pests may be a problem for us if we have warmer winters. And with the warmer springtime, we'll have earlier sowing, but as has been said, strategies have to be developed to determine when and where to sow, so that we can get to a safe crop through the critical stages. If the fall is warmer and we have later freezes, we will have better harvest conditions, drier soils, the crops will mature fast in the field, they'll dry down. We won't have so much grain drying. So those are a few impacts that I can bring to you. Here's a study that we did on the individual stations where we have long-term data, 1895 to 2009. And a blue area means a slight cooling, a red area means a slight warming. And minus 0.3 up to 0.3 over this whole time frame covers all the change that has occurred. So you'll see perhaps more red dots over on the right-hand side for the minimum temperatures, and a few blue ones on the right-hand side. So as much information as I gave you about CO2, how it is definitely increasing, you might wonder why I'm seeing these smaller changes, like 0.3 degrees Celsius, plus or minus, in our climate record. So the thing that always surprises me, this CO2 thing is real. It should show up more in the observations, but the atmosphere is a very complex thing, and we can't always pull out those signals as well as we would like to. So here are some states, Colorado showing for max and min, a 0.1 degree change for 1895 to 2009. And the base period was taken at 61 to 90. So we're showing 0.09 for Nebraska's minimum temperature. NS means, well, it's not significant. Statistically, we couldn't tell. We looked, and we don't know. Kansas, you'll see minimum temperatures 0.1. That means degrees Celsius per decade. So 0.1 per decade, 100 years would be 1 degree. North Dakota coming in 0.11, 0.15. South Dakota, not significant on the max, and 0.14 on the min. Wyoming, significant on both scores. So Kansas, Nebraska, and South Dakota, kind of not significant on the maxes, but the mins, pretty much significant, right down the line. They're warming. That means the mean is going up. Okay, so this is my ending slide. So we can go to any further questions or discussion, depending on the time.
Maybe have some time for questions.
That one,
And,
again, you're comparing to the base period 1961 to 1990. Is that anybody looked at that? With a more recent?
Oh, it's more recent.